Okay, welcome back. Part three, E naught, delta G naught, and K. All right, so we said that E naught is the driving force for a redox reaction. So if it's driving forward, then that means we have a large K. Reactants are becoming products. So there's definitely a relationship between voltage and equilibria constant. And if it's driving forward, then there's a relationship, since this is electrical energy, to Gibbs free energy, which means there's a relationship in terms of spontaneity as well. So a lot of times they'll say, well, if the sign for E naught is this, then what must be the sign for delta G naught and K? So let's take a look at this. Gibbs free energy is uh, max work. So in terms of energy, so we can define that as negative Q prime times E, which means the voltage potential in joules per coulomb, and then Q, which would be the coulombic charge. So force times distance. Q is the force, and E is the potential distance. So we just said that Q prime times E is force times distance. So the force is going to be Faraday's constant, 96,500 coulombs per mole of electrons times the number of electrons transferred, and then we can multiply that by the voltage. All right, so the relationship for delta G naught is negative NF E naught. So again, Q times E. I hate that they use Q here because we're so used to using Q as Q versus K, so I'm not going to use it, just negative NFE. So the Faraday constant times the moles of electrons transferred times the voltage. So if if E naught is positive, that means we have a strong driving force forward. So that means that delta G naught must be negative, spontaneous. Now, in terms of equilibria, K is going to be very large in favor products if we have a high voltage, and they consider anything over a tenth of a volt to be pretty high. A regular double A cell battery is 2.5 volts. So this isn't a lot of electrical current. And if you have a value that is less than negative 0.10 volts, then we're looking at very small KEQs. Oopsie poopsie. All right, so the mathematical relationship here. Remember, we said that we're dealing with, at standard conditions, 1 molar concentration, so we expect to see the gas law constant, which is there, RT over F. Now, they make the substitution. Most of the time, they're going to take a look at these at standard room temperature, which is 298 K, and if you make that substitution where R is the gas law constant for energy, so it's going to be 8.314 joules per mole Kelvin, and we multiply that by 298K and then divide by the Faraday constant, 96,500, then you get 0.0257. If you want to make that substitution, you can. I don't like using that substitution, and here's why. It kind of convolutes your understanding of the process. And what happens if they give you a reaction that's not at 298K? All right, so from our last problem, we were looking at the single displacement reaction between chlorine and bromide, and we said that the voltage for that was positive 0.283 volts. So this would be the second part of this problem. What is delta G naught and what is K for the reaction? Glad they asked. Okay. So first of all, you only have two relationships here that they're going to give you, and the one involving K and then the one involving delta G naught. So they're asking me for delta G naught. I'm going to start with that one. I have to figure out how many moles of electrons are transferred, and you can look at either half reaction. I chose the chlorine becoming chloride. 1 electron per chlorine as it goes from a oxidation state of 0 to an oxidation state of -1. But there's 2 chlorine atoms, so we multiply that by 2 and we get 2 moles of electrons transferred. Now remember, a mole of electrons, the formula for energy is well, for voltage is joules divided by coulombs. So if we solve that for energy, we get joules is equal to coulombs times volts. And so we can just substitute into negative NF E naught, 2 moles of electrons times Faraday's constant times the voltage, and I got negative 54.6 kilojoules. Now in the second part, we can use that equation they gave us for natural log of K. And again, I didn't use the 0.0257 thing. That's one more thing I got to remember. I'm just going to use the equation that they have on the equation sheet from AP Central. Natural log of K is NF E naught over RT. Then I can substitute in, and I get natural log of K is 22. And then I'm going to take E and raise it to the 22 power, and I get 3.6 times 10 to the 9th. And they got 4 times 10 to the 9th. They want 1 sig fig for some reason. Okay, so I got what they got. Good for me. Okay, the effect of concentration on voltage. If you change the concentration of your materials, then you may no longer be at K. So if we increase the concentration of our products, then we have shifted the equilibria to the right, and so therefore the reaction is going to proceed in the reverse direction, and we're going to wind up with a measured voltage less than our standard voltage. And the same thing, if our reactants are heavy, then this is going to shift from left to right, and because we're too heavy on the left side, and we're going to wind up with a voltage that's higher than E naught. So E represents the measured voltage. So measured voltage, and we can compare that to E naught based upon where our position of our equilibria is. Now, the only thing that's hard to get used to in this is that they do a heterogeneous expression for Q. So we're not going to put everything in concentration, although I would prefer that. They're going to do gases and partial pressures instead. Now, you're going to run the lab reaction under regular atmospheric pressure, so chances are your pressure, your overall pressure is going to be close to 1 atmosphere. All right, so we get the same reaction we had before for our chlorine with bromide, and they're going to standardize the concentration of the bromide, and they're going to run the reaction at 1 atmosphere. And what we're going to do is we're going to make the chloride concentration chloride concentration at 0.01 molar. Okay, so if that's the case, then our chloride concentration seems low, and if we do a Q versus K on this, we would find that our Q is too low. There's not enough product, so reactants are going to produce products, and we should get a voltage larger than our standard voltage. Okay, so here's how I did the problem. All right, so I'm going to use that relationship they gave us, and again, I'm not doing the 0.0257 substitution. I'm just going to do it the long way. And on the equation sheet, be careful. There's a base 10 equation. Avoid the base 10 equation. I don't know why, but my experience has been grading these things that people who use the base 10 equation use it because they haven't learned the notes from the chapter, and so they're looking for any equation, and then they start substituting in and they don't really know what they're doing. So stick with this natural log of Q equation. So I'm going to need Q. I already know E naught. We measured it to be 0.283 volts last time, but I'm actually going to go through the process of doing it again with the updated potentials. And as far as Q goes, we do products over reactants. So chloride squared over times bromine over chlorine times bromide squared. And then I substituted in the values they gave me, and I got 1 times 10 to the minus 4 for Q. So in order to get the overall E naught, what I did was I looked up chlorine reduction potential and the bromine oxidation potential. So I'm going to go back to that chart. And here it is. Chlorine reduction is positive 1.358, and the bromine oxidation is negative 1.066. Remember, we have to reverse the sign since this is a reduction potential, and we want oxidation potential. And with the updated values, instead of 0.283, I got 0.292 volts when I did E naught red plus E naught ox. And now I substitute into that equation for the measured voltage, and my measured voltage should come out to be 0.410 volts. They got they got 0.401 because that's using the old potential where the voltage was 0.283. Okay, so how would you deal with this Nernst equation thing in the lab? Concentrations. Well, we would set up 1 molar concentrations, and we would set up a oxidation cell and a reduction cell with little tiny electrodes, and then connect them with a wire and set up a voltmeter. So suppose we had this reaction where we're running a zinc electrode and a strong acid, and that is going to oxidize the zinc, and it's going to reduce the H plus from the acid to hydrogen gas. You know, the question would be, where's the position of that equilibria? If it favors, if we're too heavy on the reactant side, then we're going to get a voltage higher than 0.762 volts. And if we have a situation where our products are too heavy, then the reverse reaction is going to tend to occur, and we're going to get a measured voltage of less than 0.762 volts. Okay, so in the lab, we'd set up 1 molar solution, and let's say we're running the lab at close to 1 atmosphere pressure. What would be our measured voltage? Well, we would actually measure it. We would sit there, hook up the voltmeter, and we would get this measured value. And then from that measured value, we could calculate H plus, and from H plus, what would be more realistic is to calculate pH. Now, that's how your pH meters work. They're electrodes, and they work versus this issue of voltage potential. All right, so suppose we run this reaction between zinc and a strong acid, and we measure in our lab that the voltage is 0.200 volts. What must be the H plus concentration? What must be the pH of that solution? Okay, so we got a couple of things going on here. They told us that E naught was 0.762 volts, but we could look that up on a reduction potential. And these, of course, are the conditions under which we ran the lab, and then we measured E to be 0.200 volts. Okay, so first thing is, what is Q? Because position of equilibria, I'm going to have to use that equation, and Q is going to be products over reactants, so I can solve for H plus. So if I knew the value of Q, I could get the value of H plus. So here's what we do. We solve for natural log of Q, and when I do all that substitution, I get natural log of Q is 43.8, and then E to the 43.8 is 1 times 10 to the 19th. Once I do that, I can solve for H plus, and I get 3.2 times 10 to the minus 10 molar, and the pH of that would be 9.5. And they got 3 times 10 to the minus 10, and they did their substitution and the way they went about it a little bit different. All right, so in the next video, I'm going to take a look at the reverse reaction. Instead of a galvanic cell where we have a spontaneous reaction that we're harvesting energy, what if we use the energy to run the reverse reaction? So thank you very much.